Okay, we want to try out the tutorial question, and we're told that the figure below depicts a section of a process for converting toluene to benzene in a hydroalkylation reactor. We've been given the main reaction, so we have the toluene plus hydrogen giving us benzene and then methane. And then we are told that there's a side reaction that's going to produce biphenyl or diphenyl. And then we have a sample flow sheet of the process. So we would model this. Then the question gave us the composition of the feed and the two recycle streams. So that's what we have up here. And then the question gave us some conditions for some of the blocks and then a few other parameters to work with. And then the last part is, or the main thing that we are going to look at is how to do the optimization. So it says you should determine the optimum flash temperature in order to maximize the plant's profit. And we're given the expression that we should be using. Okay, so we would go through this bit by bit, and I'm taking my time because I understand that not everyone knows how to use Aspen. Some are now starting, so I'll take my time to go over it bit by bit. Okay, so the first thing we are going to do is, let me split this. We have to first enter the components we have. So when you open up Aspen, you enter the components. So I can type C7H8. Oh, sorry, it's supposed to be C7H8. So C7H8. So I want to delete and replace it, and then it says it's toluene. So I know that's fine. I can type H2, that's hydrogen, C6H6. So in case I should type this and it gives me a different compound name, then I have to come and click on find and actually find that specific compound. There's also CH4, and then there's C12H10. So we have all the components in there. Now from here we need to specify the property method. So we can click on next. So let me make this larger. We can click on next, or we can come down here to the navigation pane and click on methods. Then the property method we're told to use from the question was Peng Robinson, so Peng Rob. Then we can click on next. It brings us to the binary interaction sheet. Usually we don't need to worry ourselves with this. It's just saying that when you have certain species, certain chemical species, they can have some interactions with each other. So there are some values for those interactions or used to model those interactions. Usually we don't change these things, so we can just leave it and click on run. Okay, so now that my results are available and there are no issues, sorry, I can come to simulation and now start building the flow sheet. So one of the things that I personally advise is when you are building the flow sheet, build it unit by unit. I've seen cases where people put all the units down, connect all the streams, and then I'll try to specify each of the units. But personally, I think it's best to do it unit by unit. So let's do that. The first thing we have is, so I'll be switching between the screens. We have a mixer here. We have feed, recycle, and gas recycle coming in. Now, the question gave us the compositions, temperature, and pressure of all those three streams, right? So these three streams are coming from somewhere, they are just being brought into a mixer. If maybe we were told that a particular point, maybe from here or maybe from here, this was brought directly back in here, then we can easily do that. But then they've given us the specification, so we'll specify those three streams independently and we'll feed it into the mixer. So what I'm trying to say is that, let me just say this in another way. We have recycle here. Ideally, it means that something in the process is being brought back, right? But that wasn't told to us, it wasn't specified. So what we can work with, or the assumption we can work with, is that we just know the um, properties of these streams, so we can just specify them and feed them into the mixer and work with them. So for a case like this, I can just specify the feed, the recycle, and then the gas recycle and feed it in. If we knew where the recycling was being done from, maybe from the vapor point here and from maybe somewhere down here, we could have added the stream. But the thing about Aspen is that when you recycle a stream, it can come with a lot of errors. So normally we don't recycle a stream without doing what we call purging. So I'm just saying these things so that you can apply it later on. So what I'm trying to say is I have a sample. I tried the simulation out earlier, and what I'm trying to say is, let's say I should take this stream and recycle it back here, right? And I should try running it. I'll be expecting errors. Now, the reason why errors would occur is because I'm sending a stream back, And Aspen is going to get confused because material is going to pile up in the system. So if you ever want to recycle a stream, so this is outside the tutorial, it's just something for information. If you ever want to recycle a stream in Aspen, you have to split the stream first. So let me reconnect it so that I can show us what I'm trying to say. You have to split the stream first. So you add a split. Oh, there's even a good example down here. So the liquid stream down here, we have a split. We are sending some back and we are removing some, right? So I have a split here. I would send some of it away and then I can recycle some of it. So now when we do this, material won't pile up in the system. So this is what we do with recycle streams in Aspen. We split it up so that a material wouldn't pile up. It always has a place to come out from. So it's just something for you to take note of. But we'll just specify these 3 streams and then feed it into the mixer. So let's do that. I'll have 3 streams here. So this will be 1, 2, and then 3. So I can call this one feed. I can call this one the recycle. And then this one can be the gas recycle. Okay. Now from the question, they were all going into a mixer and then they came out. So we'll add the mixer to it and then we will specify all the streams. So we have a mixer down here. I can drop it. You see the cross whenever you click on a unit or on a stream, it comes a flow sheet, you see the crossbar. So it means that if the crossbar is active and you click, it will keep dropping the units. So in order to prevent that, after you drop your units, you can click on escape on your keyboard, or you can click this arrow button down here so that the crossbar goes away. You wouldn't repeatedly be dropping the units. So now I can join this stream here. I can just join all my streams to the mixer, and then I can set an outlet for the mixer. So from the question, the outlet stream was stream 1, so I'll just label this as 1. Okay. Now for the properties of the streams, I realized that there was a little bit of a mix-up. So what I mean by that is, if you look at it, our feed has to contain some amount of toluene, some amount of hydrogen for the reaction to occur. That's our main feed. The recycle can contain anything else. But I think in the labeling, we made this one feed and this recycle instead. So I think it's supposed to be the other way. But it doesn't really matter because you're going to specify all those streams. So for this one, I would have to split it so that I can see it better. So let's specify we'll specify feed as feed. We'll specify everything as it is. It's not really going to affect it because you're feeding everything in. So whether I give feed properties to feed or I give it to recycle, I don't know, I'm going to specify all of them coming into the mixer. So it's not really going to be an issue. So let me just click. I double click on this and I can enter the temperature. Temperature is 75 and I can change it from Celsius to Fahrenheit. Here the pressure was 569 and I can change it from bar to PSIA. So I can do that. Now I've been given the mole flow for biphenyl. So usually if we are given the mole flow for the whole stream, we can enter the value here. Then we can come here and enter the composition. But if you are given the mole flow of the individual components, you don't need to enter the value for this. So this one is for the whole stream. You are given for the individual components, so you don't need to worry yourself. You can just come here. You make sure your composition is selected to mole flow. You can enter the mole flow. So for biphenyl, it was 274.2. So I'll enter here. Biphenyl is the last one here. 274.2. And the unit is in pound mole per hour. So I'll change this to pound mole per hour. Right, so that's for the first stream. Then I can come to the next stream. So I double click on that. The temperature was 250 degrees Fahrenheit. So there's a way that we can set the temperature to be in the English standard units from the beginning, right? But that's okay. I think I can speak about it briefly. The pressure is 569 and this is PSI. Then I can specify the composition. So I change this to pound mole per hour, not per day, per hour. And then I have toluene to be 82.5, so this is going to be 82.5. I have benzene to be 3.4, so benzene is 3.4, and I have biphenyl to be 1, so I specify that as 1 pound mole per hour. Now if we wanted to set the units in the English standard units from the beginning, we would have come to setup and would have come to, I think it should be under units. set, and then we can choose the one we want. So we can select the ones we want, the ones we don't want to use. And yeah, I think that's it here. So we can do it that way, or we can come to specifications as well and then choose the units we want to work with. So I can say I want to work with English engineering units as well, right? So now I have everything here in PSI and yeah, Fahrenheit and all those things. So we can do that as well. Okay, so let's go back to the flow sheet. And then for the gas recycle here, so now it's already in the English standard units. So I can just continue from there. So temperature is 121 degrees Fahrenheit, pressure is 569, and then my compositions is already in pound mole per hour. So so let me start with what I have here. I have toluene first. So toluene was 5.3, hydrogen was 2045.9, benzene was 42.8, methane was 3020.8, and then biphenyl, there was no biphenyl there, so that's fine. So I can end it. Now that I'm done with this, I can click on next. Let me see what I've not yet done. Okay, everything is fine, so I can click on OK, and then I can run the simulation. So it's running the simulation right now, and then the results are available. So I can check my results and then be able to determine a few things if I want to. So I can right click on the units. Sorry, right click, not double click. I can right click on the units. I can click on results. It gives me the the results for the units, or I can click on stream results and it gives me the results of what is coming in and what is coming out of that unit. So I have what is coming in, all the streams coming in, and then what is coming out as well. Okay, now the next part, we are supposed to join this to a heat exchanger, and if you look at it critically, what comes out of the heat exchanger is going to a furnace, and then the output from the furnace is mixed with some other products and used. It's also going to pass to the heat exchanger. It means that whatever is going to come out of the furnace is definitely hotter than what came in. So if I'm going to use what came out, right, to pass to the heat exchanger, then it means that that is going to be the hot stream. What's coming out of the furnace would be the hot stream, and what's coming into the furnace would be coming from the cold stream. So I'm just trying to heat up what is coming into the furnace before it gets into the furnace, right? Because it doesn't make sense that what is coming in, I try to cool it before I heat it up again. It makes more sense to heat it up a bit before I heat it up with the furnace so that I use less energy. So if we think about this economically, maybe I have a stream, it's at 20 degrees Celsius, but I need to heat it to 500 degrees Celsius to place into my reactor. Instead of me having one unit that's going to heat it to 500 degrees Celsius and consume a lot of power, I can use some of the heat already in the process through a heat exchanger to heat it up a bit. So to maybe, let's say, 200 or 100 before I now feed it into the other heating unit, then into my reactor. So it means we're just trying to heat this up a bit before we feed it into the furnace, right? So I can come here, come to exchanges, click on heat X. So that's for heat exchangers, and then drop it. I click on escape. And then this is going to be the inlet for my cold stream. So if I want to rotate the block, I can click on it, right click on rotate icon, and then flip it anywhere I want to flip it. So I'll just rotate it right. Then I can give the outlet for the cold stream as well. Then let me just drop the lines for the hot stream inlets and outlets and click on escape. So this is stream 2, stream 5, and stream 6. So let me just quickly label them. This is 2, this is 5, and then this is 6. Okay, now let's continue from there. For the heat exchanger, I'll show us how to do the specification very soon. So let's look at that before we continue. So we're told here that the heat exchanger output, right, that's the inlet to the furnace, should have this temperature and then this pressure. So already, if we look at it, the pressure of everything in here, sorry, if you look at the pressure of what is coming in and the temperature of what is coming in, sorry, yes, it's coming in at a pressure of 56 and a temperature of 125. That's what is coming into the heat exchanger. But before it gets to the furnace, we want it to come at a pressure of 549. Where is it? 549, and then a temperature of 1000. So we need to drop the pressure and we need to increase the temperature. Okay, So in the heat exchanger, if I should come back, the heat exchanger, I can specify the outlet temperature. So I can say that cold stream outlet temperature, and specify it to be the 1000 Fahrenheit. So that is going to give me the pressure, sorry, the temperature. And for the pressure, it's going to drop from 569 to 549. So the pressure drop is 20 psi. So I can come up here, click on pressure drop, and then this is for the cold side. So I can either enter the outlet pressure, or I can ask it to calculate. So I'm coming to enter the outlet pressure, which I want to be 549 psia, right? And then I need to just continue with the rest of it. So this is for the heat exchanger. I've entered what the temperature for the cold stream should be and what the pressure for the stream should be at the outlet. Now from here it goes to a furnace. So a furnace, you can use a heater to do that. So I'll come back to exchangers, click on heater, and I'll drop it. I realize that for the heater, the inlet is at this side here, so I want to rotate it. So I click, right click, rotate icon, flip it horizontally, just so that it looks more organized. Now for the heater or the furnace, the specifications, we're told that the furnace outlet should be 494 psi and then 1200 degrees Fahrenheit. So these are going to be the conditions that will specify into the furnace. So there was a question someone asked me once, and the question was that the things we specify into the units, what are they affecting? So they're affecting the stream that comes out of it, right? So if I should enter a temperature and pressure here, I'm telling Aspen that whatever is coming out of this unit should have this temperature and this pressure, or should have these conditions. So you're looking at 494 psi and 1200 degrees Fahrenheit. So I can specify that as 1200 and then 494. Okay, so let me just get rid of all of these ones. Let me call this my HX, and let me call this my furnace. Okay, and then the stream out of the furnace was stream 3, so I'll call that 3. Okay, now if we go back to our flow sheet, we have this unit here. So this is going to be the reactor. Okay, and over here we have the specifications for the reactor as well. So we have the pressure, we have the temperature. So let's come to reactor, and let's choose the reactor we are working with. Now for the reactors, RCSTR, R plug, and R batch. Sorry, RCSTR and R plug are used for continuous processes that are rigorous. R batch is used for a batch process that is rigorous. What we mean by rigorous is that it's very detailed. It's not a simple model, or it's not a shortcut model. It's a very detailed model. The first 4 are usually simple models, so they don't require as much detail as these ones here. We use R gives when we want to work with what we can call feasibility studies. We want to see the possible products that can be formed. R equilibrium is if we have the equilibrium relation. R yield is if we have the yields of our products, and R stoic is if we have the stoichiometry. Now if you look at the question, we have the stoichiometry, we have the stoichiometric equation here, and we have the conversion. So R stoic requires stoichiometry and either conversion or extent of the reaction. We have the conversion as well. So our best choice is to work with R stoic. So I'll place the R stoic down. I'll rotate it horizontally so that the inlet is at this end here. Otherwise the inlet would have been at the other side, and I can give the outlets for that. So I can just place the outlets here. Now let's specify the reactor. So let me just call this reactor. Now to specify the reactor, we're told the pressure to be 494, temperature to be 1268. So let's do that. So 1268, and then this is 494. Now we can work on the reactions as well. So I'll come to reactions and I'll click on new. Now for the reactions, we have 2 reactions, and for the first one we have toluene plus hydrogen to give us benzene and methane. The stoichiometric coefficients of each of them are 1 1 1 1. So I'll come here, is my toluene plus my hydrogen to give me benzene and then methane. The coefficients are 1. So for reactants it becomes negative. So if I should just put in the number, Aspen will assign the negative automatically. Now the last thing we need to do is to specify the conversion. So we're told from the question that we are converting 75% of toluene. So that's what I'm going to choose. Let me confirm that. Yes, conversion of toluene is 75%. Now there's a second reaction, so I'll specify that as well. The second reaction, we have the benzene to form the bi or diphenyl and then hydrogen, but the coefficient for the benzene is 2, so I can specify my benzene coefficient is -2. To form my diphenyl, coefficient is 1, and then to form, I think it was hydrogen, I'll confirm its coefficient was 1. Okay, and now we also were told from the question that 2% of the benzene present after the first reaction occurs is converted to biphenyl. It means when the first reaction is done, whatever benzene is left, 2% of that is going to be converted. So I can see that the conversion here is 0.02 of benzene. Okay, now note one thing. We have this checkbox down here. It says reaction occurs in series. If this is not checked, it means reaction occurs in parallel. And if it's in parallel, what it means is that the first two reactions are happening, or the two reactions are happening at the same time. But the question told us that the benzene that is produced, right, and whatever is left. So it says whatever benzene is left after the first reaction. So it's not in parallel, it's in series. It's not like the reactions are happening together. One happens before the other. Right, so whatever benzene is present after the first reaction, so the first reaction has to occur before the second. So I need to check this because the reactions are actually in series. Okay, now if I'm done with this, I can come back and then go back to my flow sheet. So realize that we are not running the simulation to check the results because this stream here, stream 5, is actually going to come from a mixture of what comes out of the reactor and in another stream. So we don't have the chance to run it yet, right? So this is what I'm just trying to say. We are here now. We just specified the reactor. So we have to feed its outlet to a mixer, and there's going to be another stream that will join that, and then we use that to do the heating in the heat exchanger. So let's take the outlet from the reactor and send it to the mixer. The outlet was stream 4, so I'll just name this 4, and I can pick a mixer and then place it down, escape, and I can connect this here. There's another stream that we will add, but we don't yet have it, so we'll add it when we get it, right? So we can do this for now, and then we can just run to see how things are so far. If we get errors, it shouldn't be a problem because we've not added every other thing to it, right? Okay, so we can continue from here, and please be saving your work as you do it because it can get frustrating if you do all the specifications and then your laptop crashes. I've seen it happen a number of times. Okay, so now let's continue from outside the heat exchanger. It goes to a cooler and then a flash. So let's place the cooler down first. So I'll come to exchangers, click on heater, place it down. So a cooler is a heater, it's just that we specify a temperature lower than what is coming into it, and then the outlet for this. So I'll name this cooler, and then let me name this mixer 2, and I'll name this mixer 1. Okay, I think that's fine. Now let's look at the cooler specifications. The question told us that the cooler outlet was 480 and 100 degrees Fahrenheit. So let's specify that. So this was 100 and then this was 480. So that's fine. And we have to add a flash to it, so we can decide to run it if we want to. The flash, we come to separators, we click on flash 2. I think flash 3 allows for more than 2 components. Yes, so flash 2 is just vapor and liquid. Flash 3, I think, usually for vapor, liquid systems. Yeah, but most of the time it's flash 2 that we use. So we can join this here, and then we can have the top stream, the vapor stream, and then the bottom stream. That's going to be the liquid stream. So let me call this flash, and then the stream label. So we have this to be 6C, we have vapor and we have liquid. So let me just give them the same name so that if we have to reference them later, we don't have an issue. Vapor, and then this is liquid. Okay, now the question gave us an important hint right at the end. It said that the temperature of the flash must be the same as the temperature leaving the cooler. So we want the flash to be at the same temperature. So the cooler is just going to cool whatever products we have here so that some of it can condense. Then after it condenses, we just send it to the flash. We don't change the temperature or pressure so that whatever vapor and liquid we have, we can separate it. right? So I can specify the same thing. So this is going to be the 480 and 100 that we have over here. So 480 psia and then 100 degrees Fahrenheit. Okay, let me see if I did the same thing for the cooler. Now you realize that before we continue, I just want to say something. You realize that we are going to do optimization, right? And if you look at the question, the optimization, we are going to have the duty of the cooler changing. That means the temperature will change, because the question even said determine the optimum flash temperature. So it means the flash temperature itself would also be changing for the optimization studies. Now the cooler and the flash out have the same temperature, so that means that if the optimization should run and the flash temperature should change, am I going to continue changing the cooler temperature? No, right? So we are coming to use what we call a transfer block. I'll show us how to use a transfer block. If the question was saying that the cooler temperature is supposed to be fixed at the 100 degrees Fahrenheit and only the flash temperature should change, then that is fine. We can change the flash temperature. We don't need to worry about the transfer block. We can let the optimization run on just the flash temperature. But the question said that the temperature of the flash tank must be the same as the temperature leaving the cooler. So it means that when whatever temperature the flash should have, the cooler should have the same temperature. Okay. Now we can't be changing it all the time, especially when the simulation is running, when the optimization is running. So we use a transfer block. What a transfer block does is it picks one parameter from one block and applies it to another block. So I can come to manipulators, click on transfer, just drop it anywhere. Right, I can click on escape, then I double click on this. Now what I want to say is that I'll come to block or string variable. So I want to specify a block variable. I want to specify the temperature of a block. That's the flash, right? Or let me say the cooler. So whatever temperature the okay, I think let me use the flash. It's fine. So I want to work with the temperature of the flash. So the flash is a block. It's not a stream I'm working with. So I didn't choose stream variable. It's a block I'm working with. So I chose block variable. So block variable. Then the block I'm interested in is the flash. And then the variable I want is the temperature. So temp. Okay. And then what I want it to be transferred to. So I can click on to. Then just select new here. Once again, it's a block. I'm transferring it to the cooler, which is a block. So I can click on block variable. The block I'm interested in is the cooler, and I can also see that I want it to I want to transfer it to the temperature of the cooler. So now whatever temperature of the flash I specify to be the same temperature as the cooler. So let me show as what I'm saying. Let me run this. Let's see, the flash temperature should have been changed to 200 degrees Fahrenheit, right? Now let me run the simulation once again. If we look at it, the cooler temperature, we have the original thing in there. But if I should check the results, so let's check the stream results. If I should check the stream results, the inlet was at this, but the outlet is at the 200, because the 200 was for the flash. So even though 100 is specified in the flash, it's going to come out at 200, which is, sorry, 100 was specified in the cooler. It will come out at 200, which was the flash temperature. So this is how the transfer block works. It would overwrite whatever I've done here. It still needs to be done. If this was blank, it would tell me it's incomplete. So there still needs to be something there, right? But if I use a transfer block, it would overwrite this and apply the transfer that I have specified. Okay, so that's just something for us to learn. So from here we can continue with the rest of the flow sheet. So we have a splitter here. So I'll place my splitter down. So I'll come to missions and splitters, click on F split, and then so F split is used to split based on the fractions, right? S split, I've not really used S split before, yes, but I think S split is good enough. So I can join this here, and then I can have my two outlets. So I have one, and then I have the other. So let me just bring this down, and then the streams, I can label them as products and PF. So this is products, and then this here is PF. So this is PF. Okay, now let's look at how we are specifying the split. Okay, it's down here. The splitter block after the flash tank has a flow split fraction of 0.8 of product stream. So what it means is that if I should come here, the product stream, this should be the split fraction for the product stream should be 0.8. and Aspen would know what the other. If it's two streams, the total fraction should be 1. So if I specify 0.8, Aspen knows the other is 0.2, so I don't even need to stress on that. So that's for the split, right? Then from there we can carry on with the pump. So this is a pump, so I can come to pressure changes, click on pump, and then drop it. Once again, the inlet is at the other side, so I'll rotate it. So flip horizontal, and I can place the outlet for the pump. So when I'm done with this, I'll say a few things that I think are necessary for us to know. The pump specifications, we were told that the outlet pressure should be 494, and then the outlet temperature should be 82.5, right? But if we should click on the pump, realize that it is just the pressure we can really specify from here. We don't have the liberty to specify the temperature, right? So I'll specify the pressure as given to me in the question. The pressure was 494, so discharge pressure 494 psie. So the things I wanted to say, you see how sometimes the question gives extra specifications, like we have the temperature here. It could be, right, that before this comes in, so you can add units to the flowsheet if you have to make sure everything works as it is supposed to. If it was necessary that it should come out at 82.5, right, this is a flash, it's not, so this is a pump, it's not a heating unit. What we can do is that we can add a cooler to this side here and then cool the stream to 82.5 before we pump it, right? There's another way. So we can come to exchanges, because here realize that it's temperature and pressure that are changing, and exchanges can change temperature and pressure, and we can work with this unit up here. So this is going to also be a pump, right? But then this is going to be a pump that allows for changing temperature and changing pressure. So I'm just showing you all these two. It's either you specify the normal pump and then just specify the, what's it called, the pressure, or you specify this pump from the exchangers and specify both pressure and temperature, right? If you specify the normal pump, then you have to add the cooler so that you can cool the temperature down to the 82.5 before you pump it, so that the pump will have those outlet conditions. So let me delete this and let me use this one instead. Let me flip this and let me join this here. Okay, well, this is the outlet rather, so let me join this one here. Okay, now just in case you want to make your work more organized, right, let's say the lines are all over the place, you can do Control A. So Control A will select everything, then use Control B. Control B would shift it around to make it a little bit more organized. So that's just by the way. Yeah, the other thing I wanted to say before we continue is that the question also gave us the duty for the heater. That's the 60 BTU. So the overall heat transfer, that's the 60 BTU per hour feet square degree Fahrenheit, right? But remember that we are going to have a certain inlet coming here, and then we have the cold stream as well. So it's possible that the value might not be exactly the same. If you wanted to specify the that value instead, the u instead, right, you could have come here, clicked on constant u value, and then specified that, so that you can get it to be the same. If you should let Aspen just run, it would do its own calculations. So for the heat x, right, you come here, click on u method, and then over here I can specify the 60, so that's going to be the u value, and then keep this in BTU per hour square feet Fahrenheit, right? So that was the other thing that I was supposed to also show us. So I think we've catered for all these conditions here. So the last thing we need to do is the pump. What comes out of the pump, we'll call that stream quench, and we feed it back to the mixer that we were using earlier before we went to the heat exchanger, right? So let me send this stream all the way to the mixer over here. Let me try and arrange it a little bit better. Okay, I think this should be fine. And now we have this down. Oh, we didn't specify the pump, sorry. So the temperature here it was 82.5, and then the pressure was 494. So 82.5 and then 494. Okay, so we've met all the conditions now, so we can run. and we don't have any errors. We thank God for that. So this is just to set up the flow sheet and meet all the conditions from the question, right? In order not to make the video too long, I'll end this first part here, and then the next part I'll continue with the optimization itself. So okay, I think I didn't want to handle this first part here, but I'll still show us how to do the material and energy balance, and then we'll continue from there. So I would solve the next two questions in the next video, and then we'll take it from there. Thank you very much for your time.